This video is all about solutions. So we describe solutions as homogeneous mixtures, mixtures that are the same throughout. So a homogeneous mixture is a solution. And homogeneous mixtures really appear to be all one substance, though really they do contain multiple materials. So let's look at our example here. We've got our water solvent, or our solvent at least looks like water in this blue beaker, or this beaker of blue liquid. And, so the pale blue color makes us think that it's probably water. And then we've got this green solid solute. So let's say that we're dissolving, a green colored compound into our water solvent. And then we end up with this green solution, and it looks all the same throughout, like it's just one substance. When they look all the same throughout like that, we call this a homogeneous mixture or a solution. So what are the components of solutions? Well, the solute is the dissolved substance. So our solute is the green solid. It seems to disappear. It takes on the state of the liquid solvent in this case. So a solute takes on the state of its solvent, or can take on the state. And the solvent is the substance the solute dissolves in. So in this case, it looks like our solvent is water, and it's the water that our green solid is dissolving in. Our solvent does not appear to change state. And our solvent is the component present in the greater amount, in the highest percentage. So we usually say that the solvent is present in the greater amount, and the solute is present in a lesser amount. And solutions in which the solvent is water are called aqueous solutions. So we have lots of times in life where this aqua prefix is used to mean water. I mean, we have aquatic centers with pools. We have aquatic life, that marine life or life in water. We have aquifers that contain water. We even have the brand named Aquafina for, bottled water. Agua means water. So lots of places that we can relate to in everyday life where we know that AQU is the start of that water reference. And so an aqueous solution is just a solution where water is the solvent. Okay. Oh, I'm right in the middle of this. Let's move me. So let's talk about some different solutions and what phases they can be in. You can have gaseous solutions. So you could have a gas solute and a gas solvent. An example is air. Air is mostly nitrogen, so that would be our solvent. And then it's 20% oxygen or just under 20% oxygen. You might call that a solute, but it's a mixture of nitrogen and oxygen. So you can have gaseous solutions. You can have liquid solutions where liquid is the solvent. Think like water, for example. But you can have gas bubbles dissolved in liquid, like in soda. There's carbon dioxide dissolved in water, in pop or soda, And then you could have a liquid-liquid solution. The example here, we've got vodka or ethanol in water. So alcohols are infinitely miscible in water, and ethanol is that beverage alcohol that's found in beer, wine, or liquor, or vodka for here. You could have a solid dissolved in a liquid. So in seawater, for example, we know we have sodium chloride dissolved in water. In our example, it looked like we had a green solid dissolved in water. You can even have solid-solid solutions. So classic examples of solid-solid solutions are all of our metal alloys. Metals, being alloyed to be stronger and have better properties were really important historically. So for example, brass is zinc and copper. Bronze is an alloy of tin added to copper. So when we alloy metals or make mixtures of metals, we have to heat them up and mix them up evenly, but these are often improve the properties of the metals. So lots of good reasons to make solutions. So how do you know if one substance will dissolve in another? Well, chemists, we have a rule of thumb. It's like dissolves like. So a chemical will dissolve in a solvent if it has a similar intermolecular force to the solvent. So things will dissolve if they have similar intermolecular forces to the solvent. So in other words, polar molecules will be attracted to polar solvents. Um, so what are things that are polar? For example, sugar is polar and it will dissolve in polar water. Ethanol is polar and it will dissolve in polar water. That was the vodka that we saw in the previous slide. The beverage grade alcohol will dissolve in water. NH3 or ammonia will dissolve well in water. That's what's pictured here. Our NH3 is polar. So our NH3 has it has slightly positive ends. Let's look at it here. Our NH3 is going to have slightly positive hydrogen ends, and those will be attracted to the slightly negative ends of water. And the same is true for the slightly negative part of the ammonia. That will be attracted to the slightly positive part on water. And so we'll have positives attracted to negative from the ammonia to the water molecules. And that will help them dissolve. So in polar substances, the partially negative portions of one molecule are attracted to the partially positive portions of the other. What happens with nonpolar molecules is they will only be attracted to nonpolar solvents or dissolve well in nonpolar solvents. For example, beta carotene is a big nonpolar molecule. It's about, it's C40H56. And so all of these carbon-carbon and carbon-hydrogen bonds that it's composed of are nonpolar. The C to C, electronegativity difference, that's going to be 0. All of the C to H bonds, those have a difference of only 0.4. And so these are really small electronegativity differences. So they're all nonpolar bonds. And they're not going to be very water soluble at all. Water is really polar, and so since beta carotene only has non-polar bonds, it won't be water soluble. It won't be able to, it doesn't have any partially positives or partially negatives to line up with water and help it dissolve in water. So it's going to only be soluble in fatty nonpolar tissue, for example. So that's what we would refer to as a fat-soluble vitamin because it doesn't have any polar groups, like our sugars, which have lots of OHs, for example. So the OH groups in sugar really help it dissolve. We also saw OH present in our alcohol. So these O to H, and here we've got an NH3, we've got N to H bonds. So those all happen to be superpolar OHs and NHs that allow them to dissolve in water. And in the absence of those, substances like beta carotene will only be soluble in other nonpolar substances, like our fatty tissues that are also nonpolar. I've got to move myself. So ionic substances are next. Ions are attracted to polar solvents. The reason being ions are full-on plus and minus charges, and so they're going to be attracted to the delta positive, the slightly positive, and slightly negative in polar solvents. So ionic compounds dissolve in water, many ionic compounds, not all of them, but a lot of ionic compounds dissolve in water because water can surround those positive and negatively charged ions. For example, here is a picture of chlorine and it's Cl minus, so it's being surrounded by the delta positive ends of water. And so the positive H's of water are going to be attracted to the negative chlorine. Na plus, so that was because it's Cl minus. The sodium is positively charged, Na plus. It will be attracted to the negative oxygen end of water, get totally surrounded. And that actually pulls those ions off the crystal one by one by one. So again, positive sodium, here's more of a close-up, attracted to the slightly negative oxygen end of water. Negative chlorine attracted to the slightly positive hydrogen end of water until those And so basically, these solvent to solute attractions overcome the actual ion-ion forces. So when materials dissolve, the solvent molecules surround the solute particles in that solvation process due to the solvent's attraction for the solute. And that whole process is called solvation. And that really allows sodium chloride or salt to be soluble in water. Most ionic compounds are, but not every single ionic compound is going to be soluble in water. So we'll use solubility tables and we'll review those in just a little bit as well. So here let's practice. Let's decide if each of the following will be significantly soluble in water. So the first one we've got is potassium iodide. So we have to ask ourselves, okay, is this ionic? Is this polar? Is this nonpolar? Potassium iodide is, it starts with a metal, potassium, and a nonmetal iodine, and we've got a plus charge and a minus charge. So this is ionic. Since it's ionic, it'll be soluble in water. Next up, methanol. Now, it's good to notice that methanol has this OH. Whenever we've got OH, NH, or FH, we've got the really polar group. I mean, so polar it can hydrogen bond. So that's really polar. It's like water, so it'll be soluble in water because like dissolves like. Remember that, the H on the methanol will be attracted to the O on water. Oxygen will be slightly negative. This H on methanol will be slightly positive. And so those two will be attracted to each other, positive to negative. Now we look at methane. That's just carbon bonded 4 times to hydrogen. So, if we wanted to draw that out, we've just got a carbon with 4 hydrogens. So we've got 4 C to H bonds. If we check our electronegativities, carbon's a 2.5 minus hydrogen here is a 2.1. And so when we subtract their difference, we've got a really small electronegativity difference. This is nonpolar, and since it's nonpolar, it would not be water soluble. Same thing with metals. Now, we didn't specifically give those as an example, but a metal like copper or aluminum shouldn't be water soluble, right? I mean, we make pipes out of copper. We don't want them to be water soluble. We make cans out of metals like aluminum, not water soluble. So, some of our alkali metals react with water, but in general, most of the metals like gold or silver that we use for jewelry or like copper or aluminum that have a lot of everyday uses generally are insoluble. Again, some metals do react with water, but in terms of just dissolving in water, we generally say that a lot of these metals are insoluble. Okay. Next up, we want to talk a little bit about solubility curves and like the maximum amount of things that can dissolve. So the maximum amount of solute that can be dissolved in a given amount of solvent is called its solubility. So unsaturated solutions, you can still get more to dissolve in. They can dissolve more solute. They have not yet reached their saturation level or sort of their max capacity. Whereas saturated solutions do have the maximum amount of solute that will dissolve in that solvent at that given temperature. So if a solution is saturated and you try to add more in, that extra solute you add just sits at the bottom, won't do anything. If a solution is unsaturated, it hasn't yet reached its capacity, you add more solute in and it looks like it's gone. Now it's not gone, it's just all dissolved because it was not yet saturated. So think of saturation as a maxed capacity, and unsaturated means you are not yet reached that. Okay, so let's look a little bit at solubility curves. I have to find a good spot for me. How about right in the middle? Here we go. So the solubility in solvent really is temperature dependent. It depends on the temperature, and that's what this graph is showing. This graph shows us that the solubility of solids generally increases with temperature. So that's true for solids. Solids, you heat up the solution if you want to get more to dissolve in it. If you've ever made candies with sugar at home and made sugar solutions to make any sort of caramel or hard candy or things, you know that you heat that solution up to get more sugar to dissolve. So let's dive in and look for an example. The solubility of KCl, potassium chloride at 10 degrees Celsius. So we go to the 10 degrees Celsius and we go up to this KCl line. Looks like it's this dark blue, about right there. And I would say it's right at about 30 grams of KCl. Now we should tell everyone what we've dissolved it in. It's 30 grams of KCl in 100 grams of water. Goofy line, but per 100 grams of water. So that's pretty important too, that we tell the reader what we're dissolving in this. What we're dissolving this in, 100 grams of water. So if more KCl were added to 30 grams in 100 grams of water, the extra would not dissolve because it's already been saturated. So it's that picture of you add more in and it just sits on the bottom if you tried to add more in. So let's look at a little practice. What's the solubility of KCl at 80 degrees? Okay, so we're going to go up to 80 degrees and figure out how much can dissolve. Okay, so I would say it looks like we're maybe just above the 50, so maybe about 51 grams of KCl per 100 grams of water. So just over 50 grams of potassium chloride will dissolve at that temperature at 80 degrees C, so 51 grams. Next up is 40 grams of KCl in 100 grams of water at 80 degrees C, unsaturated or a saturated solution. Okay, I like to find the temperature first. I like to go to the x-axis and find 80 degrees Celsius, and then we need to look for the KCl line. Now, we just said 51 grams can dissolve. It says, is 40 grams in 100 grams an unsaturated or a saturated solution? So, I mean, if you want to look for the dot, 40 would be down here. We know we can fit 51 grams. So if we're at 40 grams, we are not yet saturated. That's an unsaturated solution. The next question says, is 40 grams of KCl at 50 grams of water at 80 degrees Celsius, unsaturated or saturated solution? Now, that's a little trickier because what we want to notice is our basis is twice this amount, right? Our whole graph is based on everything being double this amount of water multiplied by 2 to get 100 grams of water. So we need to think about this amount of KCl doubled. We need to think about what if 40 grams were doubled, you'd actually have 80 grams of KCl in 100 grams of water. So we're really asking, is 80 grams of KCl, like if we want to change the problem is really asking, is 80 grams of potassium chloride in 100 grams of water unsaturated or saturated? So we go to 80 degrees and we ask ourselves, if we had 80 grams, we'd be way up here, way past saturation. So the solution is for sure saturated, and a bunch of extras actually sitting at the bottom. You know, the first 51 grams will dissolve, and then all of this extra is actually just at the bottom, hanging out, unable to dissolve. Okay, I'm actually going to erase that just so we can see a little better. And then our last question is 40 grams of potassium chloride in 100 grams of water at 20 degrees Celsius, unsaturated or saturated? Okay, so our basis is back to 100 grams, but now we're at 20 degrees Celsius. And then we'll find our 40 gram line. Notice how now we're above the potassium chloride line down here in the dark blue. So if we're at 40 grams, we're already saturated. Okay, so that's your basic terms for solutions, including solute and solvent, saturated and unsaturated, and really how to read solubility curves.